Now let me introduce binary regression models. So let's say we have a binary variable y, and there are two states, okay? 0 and 1. So here, 0 could mean, well, did not vote, and 1 is voted. 0 could mean did not participate in the labor force, and 1 denotes labor force participation. So 0 could be a failure of certain events, and 1 is a success of an event, depending on how failure and the success are defined respectively. Sometimes we can reverse failure with success. So it doesn't matter how we code it what we coded as 0, what we coded as 1. And if we reverse it, the results are mathematically equivalent. So here is we have observed a binary variable y, right? And we observed two states for the observed y. Correspondingly, we can assume there is a latent variable y star here, ranging from negative infinity to positive infinity. And there is this threshold. Tentatively, we can make that threshold 0. And let's say for y star from negative infinity to 0, or that threshold, later on we will learn that, we observe y to be 0. Note that y star is an unobserved latent variable. So it is unobserved. We only assume its existence. Same thing for y, observed y equal to 1. We have range from 0 to positive infinity. So if y star, this latent unobserved variable, continuous variable, ranges from 0 to positive infinity, we observe 1. And we have a couple examples, right? Y is observed in two states, could be a woman in the labor force. So y equal to 1 is in the labor force, right? And then y equal to 0. That is when this woman is not in the labor force. Note that not all women with y equal to 1 are in the labor force with the same certainty, right? Some women in the labor force with certainty because she's young and she has a high level of education and she has this motivation to participate in the labor force. Whereas there's another woman who is relatively well educated, who has one child, and she's probably balancing between work and family and trying to figure out if she still wants to stay in the labor force. So for the second woman, the certainty is low. So here, so for the first woman, it's y star probably somewhere here. And for the second woman, actually is probably the propensity or the y star is pretty close to the threshold. A little bit force, a little bit factor here could push her through the threshold and become 0 for observed y. That is, she could become inactive in the labor force or not participate in the labor force. So one woman might be very close to the decision of leaving the labor force. Another woman could be very firm in her decision. That's exactly what I was talking about. So y star give us the idea of kind of propensity likelihood, which is unobserved. So y star is unobserved and latent continuous variable, and y is what we observe. So y star is not in our data set. We will never, ever have information by y star. But here, we make this assumption to set up some relationship so that we can derive the model. So the idea of a latent y star, so again, this unobserved y, continuous y, there is an underlying propensity that generates the observed state. We cannot directly observe y star, but at some point, a change in y star results in a change in what we observe. Okay? For example, as the number of young children in the family increases, a woman's propensity to work would increase. At some point, the propensity crosses a threshold that results in a decision to leave the labor force. Okay? Then what would push an individual to cross that threshold? Well, a lot of times predictors, right? So here, the example would be the number of young children, right? Other possibilities would be, for example, the husband has medium to low level of income, but not participate in the labor force. Here's a question for you to think about. Can all binary outcomes, well, not necessarily outcomes, okay, but could be predictors, any binary variables, be viewed as manifestations of a latent variable? So let me start deriving this model. So let's assume there's this structural model, okay? And this structural model is for y star. So we begin with y star. So y star is equal to x beta plus epsilon. That's a very commonly used structural model. And x here denotes the vector of predictors. Beta is a column vector of slopes plus the intercept usually. Not necessarily we have to have intercept, but usually. Then epsilon is disturbance term, which is a collection of factors that somehow are not taken into account in our analysis. So it could be a labor force participation, right? And here we replace this y star with labor force participation star, right? They refer to the same thing in this case. And, you know, intercept, number of kids and age, right? Plus a error term, okay? And we have this measurement model, okay? In addition to the structural model, okay? Relating y star to y. That is, y star is linked to the observed y. Again, I have to remind you that y star is unobserved, okay? So y star is linked to the observed y by the measurement equation, okay? So for y star greater than threshold number, in the last slide, we use 0 as the threshold value, but it could be any value in theory, right? So it's called tau. So when y star is greater than tau, we say y, the observed y, is equal to 1. When y star smaller or equal to tau, then y equal to 0. Fair enough, right? So y star is kind of propensity. It's on a continuum. When it hits certain threshold, okay, it's going to change its state. And tau is called the threshold or cut point. Pretty commonly used term in categorical data analysis. And also, we make the identify assumption that tau equal to 0. And people might ask why tau has to be equal to 0. Well, here it's just an assumption we make. And later on, you will learn that actually it doesn't matter what tau equals to. It only affects the estimation of the intercept. It does not affect the estimation of any other slopes. Okay? And this identifying assumption makes the estimation possible. And this assumption, know that, is similar to the assumption, the conditional mean equal to 0. Conditional mean equal to 0. And this assumption also makes the estimation of intercept possible. So let's take a step further. So step one, since y equal to 1, y star equal to 0, right? This is assumption we make. This is called identifying assumption. Then, equivalently, the probability equal to y given same set of x is equal to the probability y star greater than 0 given x, right? They're equivalent, so from here to here, right? Logically. And we can substitute y star with x beta plus epsilon. What we get? So we're going to do this. What do we get? Well, the probability y equal to 1 given x is equal to this one and equal to this one, right? The only thing I did was to replace x beta plus epsilon, replace y star with x beta plus epsilon, right? And that's, again, assumption we made, the structural model. Okay? And what we're going to do is, for this equation here, we're going to make a pretty simple algebraic rearrangement, right? Then we will get epsilon greater than negative x beta, right? So we move this term to the right-hand side. Well, what we're trying to get at actually is a cumulative density function. That is, we want to have equation like the probability of epsilon smaller than something. Why? If you remember the introductory statistics course, right? You learn z-score. And how you calculate the probability for a z-score? Well, usually have a graph like that, right? And if you remember introductory statistics course, so this is z distribution, right? And you're going to say, well, what's the probability for z smaller than a value delta? And you're going to have the probability what? Delta, right? And that means you're trying to figure out the probability for z smaller than this delta. And next step you're going to do is you flip through the pages of the book and turn to the very end of that section and try to find the answer, right? Because in those tables, they have the probability for z smaller equal to a certain number, delta here. Okay? So that's the general idea about a cumulative density function. Well, since CDFs, CDF here stands for cumulative density function, express the probability of being less than some value, we must change the direction of the inequality. So the probability y equal to 1 turns into the probability epsilon smaller equal to x beta, right? Because if we multiply both sides by -1, the inequality sign switches, right? Switches. And then we can use this cumulative density function to denote this relationship. So